Hi everyone, welcome to Rick Info. Today we are stepping into a fascinating, almost mysterious world where particles behave like waves. In this video, we'll explore the beautiful and deeply logical journey of quantum mechanics, a world where positions are never exact and probability defines reality. We will travel from something as simple as vibrating string to the very structure of the atom. To begin with, think about a guitar string. When it vibrates, it creates waves. Here is the surprising part. The same wave idea describes electrons in atom, which defines chemistry. Naturally, a question arises: can particles behave like a wave? In classical physics, the answer was no. Particles and waves were considered completely different, but as experiments improved, this clear distinction began to collapse. At this point, science took a revolutionary turn. Instead of forcing electrons to behave like a particle, scientists began asking a new question: what if electrons also have wave like properties? This idea was formally proposed by the scientist de Broglie. He suggested that every moving particle is associated with a wave. He even related a particle's wavelength to its momentum. This was the bold and unexpected idea at that time. He also gave a mathematical relation connecting wavelength with momentum, where wavelength equals Planck's constant divided by momentum. From this, we understand that a particle's wavelength depends on how fast is it moving. So, matter is no longer just particulate in nature, it has an inherent wave character. The de Broglie equation tells us that every moving object has a wave associated with it. Its wavelength depends on momentum, that is, mass into velocity. For a ball, the mass is large, so the wavelength is extremely small and unnoticeable. But for an electron, the mass is tiny, so the wavelength is significant. That's why wave behavior is visible for electrons but not for everyday objects. A theory counts when an experiment supports it. That's where Davison-Jomer experiment comes in. In this experiment, electrons were directed towards a metal surface. Instead of behaving like particles, they produced a diffraction pattern. Diffraction is a property of wave. So this experiment clearly showed that the electrons exhibit wave-like behavior. This leads to an important insight. If electrons have a wave nature, then their behavior cannot be explained using simple particle trajectories. Instead, we must think in terms of wave patterns, and this completely changes how we visualize atoms. Now that we know electrons behave like waves, the next step is to describe these waves mathematically. This is where quantum mechanics truly begin. Here comes a mind-blowing concept, the iconic Schrodinger's cat, a conceptual experiment where multiple outcomes exist at the same time until a measurement is made. It reveals the probabilistic nature of quantum systems. Sounds strange, isn't it? This is how nature behaves at the subatomic level. Erwin Schrödinger developed an equation that describes how these electron waves behave. This equation forms the foundation of quantum mechanics. Although the full mathematical form of the equation can be complex, its purpose is very clear. It tells us how the wave associated with an electron involved in three-dimensional space. The solution of Schrödinger's equation is called the wave function, denoted by psi. This wave function contains all the information about the electron. However, the wave function itself is not directly observable. What we can interpret is the square of the wave function. This gives the probability of finding the electron in a particular region of space. So instead of saying where the electron is, we describe where it is most likely to be found. At this point, quantum mechanics feels very different from classical physics. Now let's connect this idea of waves to something more visual and familiar. When waves are confined to a fixed region, they form standing waves. When two waves travel in opposite directions, they begin to overlap. This process is called superposition. As they merge, a new pattern forms called a standing wave. Unlike moving waves, this pattern appears stable in space. In this standing wave, some points remain completely still. These are called nodes. Between them are the regions of maximum vibration. These are called antinodes. So, from simple wave merging, we get a structured pattern of nodes and antinodes. Standing waves are not arbitrary. Only certain wave patterns are allowed, those that satisfy the boundary conditions. This means not all energies are possible. Applying this idea to atoms, electrons behave like standing waves around the nucleus. This is the key concept in quantum mechanics. Now let's connect the dots. The standing wave nature of electrons imposes strict rules on their energy levels. As a result, energy becomes quantized. Electrons can only occupy specific energy levels and not values in between. Another important consequence is the formation of orbitals. Orbitals are three-dimensional regions in space where probability of finding an electron is high. For a deeper understanding, you can watch my detailed video on orbits and orbitals. You will find the link in the description and also in the pinned comment. Moving on. A further important consequence is the appearance of nodes. These are the regions where probability of finding an electron is 0. We will explore these in detail very shortly. Now that we have orbitals, the next question is how to describe them precisely. For this purpose, we use quantum numbers. These are the set of values that completely describe an electron in an atom. There are 4 quantum numbers: principal, azimuthal, magnetic, and spin quantum numbers. Each one adds a specific piece of information about the electron. Quantum numbers define the energy, shape, and the orientation of orbitals. Each electron has a set like identity code. Together, they map where an electron is most likely to be found. The first is the principal quantum number, represented by the letter n. It determines the energy level and the size of the orbital. N takes the values 1, 2, 3, 4 and so on. As its value increases, the electron is found farther from the nucleus. Next is the azimuthal quantum number, denoted by L. It defines the shape of the orbital. Its value range from 0 to n-1. These values determine the type of orbitals S, P, D and F. Based on the value of L, we get different orbitals. L is equal to 0 gives S, L is equal to 1 gives P, L is equal to 2 gives D, L is equal to 3 gives F orbital. Each type of orbital has a distinct shape. For example, S orbitals are spherical while P orbitals have directional lobes and so on. The third quantum number is the magnetic quantum number, represented by M. It describes the orientation of the orbital in space. Its value range from -L to +L. So, for each orbital type, there are multiple possible orientation. This is why a single subshell can have multiple orbitals. Now, to understand how it works, for S subshell, where L is equal to 0, M is 0. So, there is only one orbital and it is directionless. For P, where L is equal to 1, M takes the values -1, 0, +1. So, there are 3 orbitals. For D, where L is equal to 2, M takes values -2, -1, 0, +1, +2. So, there are 5 orbitals. And for F, where L is equal to 3, M takes the values -3 to +3. So, there are 7 orbitals. This explains why multiple orbitals of the same type can exist in different spatial directions. Finally, we have the spin quantum number, denoted by M, subscript S or simply S. It represents the intrinsic spin of the electron. It can take only 2 values, +half or -half, often described as clockwise and anticlockwise spin. They represent 2 possible spin states of an electron in an orbital. So, even within the same orbital, 2 electrons can exist as long as their spins are opposite. Thus, each orbital can hold 2 electrons with opposite spins. Let's consider 2p subshell. Here, n is equal to 2 and L is equal to 1. So, the magnetic quantum number M is -1, 0, +1, giving 3 orbitals, 2px, 2py and 2pz. And for each orbital, the spin quantum number ms can be plus half or minus half. So in total, these quantum numbers fully describe all electrons in the 2p subshell. Quantum numbers help us understand how many electrons can occupy orbitals at different energy levels. Once you recognize the pattern, electron arrangement becomes systematic. And importantly, you should appreciate that 2n squared rule given by Niels Bohr is neither violated nor outdated. It naturally follows from the quantum numbers. As a result, quantum numbers provide the link between the shells, subshells, and orbitals. Therefore, quantum numbers are fundamentally very important. We can describe its energy, shape, orientation, and the spin of an electron. They form the foundation of understanding atomic structure and electronic configuration. In fact, you can think of quantum numbers as a blueprint or even a barcode of an electron's unique identity in an atom. To make it cleaner, imagine locating an address. You move step by step from a city to a street to house, finally to the room. In the same way, quantum numbers narrow down the position and the state of an electron in an atom. Quite fascinating, isn't it? Okay, now that we can understand how to trace an electron, let's return to nodes and understand them in detail. Nodes are regions where probability of finding an electron is 0. These nodes are directly related to orbitals. Each orbital has a specific number and arrangement of nodes that defines its shape and structure. Based on their nature, nodes are of two types: radial nodes and angular nodes. Radial nodes depend on the distance from the nucleus. They appear as spherical regions where the probability becomes 0. The number of radial nodes is given by the formula n minus L minus 1. Consider 3s orbital where n is equal to 3, L is equal to 0, where radial nodes is equal to 3 minus 0 minus 1 is equal to 2. Angular nodes depend on direction. They are related to shape of the orbital. These are regions, usually planes or cones, where the probability becomes 0 due to orientation. The number of angular nodes is equal to L, the azimuthal quantum number. Let's understand this for p orbital. For a p orbital, L is equal to 1. So the number of angular node is equal to 1. This means there is one nodal plane passing through the nucleus, where the probability of finding the electron is 0. This nodal plane divides the orbital into two lobes of opposite phase. Nodes are not just abstract points, they determine the very shape of orbitals from the spherical s orbital to the multi-lobed d and f orbitals. The total number of nodes depends on the energy level. By combining radial and angular nodes, we get the complete nodal structure. These patterns are not random. They follow clear mathematical relation based on quantum numbers. As shown in these images, for 1s, no nodes; for 2s, one radial node; for 2p, one angular node; for 3p, one radial and one angular node. When we compare radial and angular nodes, radial nodes depend on distance from the nucleus, while angular nodes depend on direction in space. Together, they determine the structure and shape of orbitals. Here we begin to see the symmetry and order in atomic structure. Now, take a moment to zoom out and watch the incredible journey we witnessed. We started with the waves in a string, moved to wave nature of electrons, developed a mathematical model, and arrived at orbitals and quantum numbers. All of this shows one powerful idea. The same mathematical principles govern both simple vibrations and complex atomic structures. This is the beauty of science, from music to matter. Thanks for watching. Let's continue exploring more concepts in atomic structure in the next video. Any guesses what's coming up next? Stay curious. Bye.